In section 1.2, we learn about evaluating limits graphically, and we talk about the limit as being where the function is headed, not necessarily its actual value. So in section 1.3, we're going to work with limits analytically. And so to start off, let's just review what we mean by a determinate versus an indeterminate form. So 1 divided by 0, if you take out a calculator and divide the number 1 by like the smallest decimal you can think of, that number just keeps getting bigger and bigger and bigger. So 1 divided by 0 is infinity, essentially. 1 divided by infinity, well, that's just the number 0. So when we're like evaluating a limit and we see something like that, any number divided by a huge, huge number is 0. So 0 divided by infinity would also be 0. And if we were to flip that, infinity divided by 0 is infinity. So these are all things that if we observe this when we are analyzing a limit, these are all things that we know. These are determinate forms. We also have some indeterminate forms. So 0 divided by 0, that is neither 0 nor 1 necessarily. It just means that we don't know. So we have to actually, when we're evaluating a limit and we get 0 over 0, we're going to have some other things that we have to do here. So we'll circle back to some of these later, but for today, if we get in a limit a 0 over 0, or an infinity divided by infinity, we're going to have to do some thinking with some of those. All right, so we talked about discontinuities in our last section. So just a reminder, if I have a function f and I evaluate f for some particular value a, if I yield 0 over 0, that is a hole in the graph. So 0 over 0 indicates that a function has a hole in the graph. On the other hand, any non-zero number divided by 0, so that's the letter B, if I plug that in, that indicates that I'm at the location of a vertical asymptote. So I know you did that in Algebra 2 last year or whenever you took Algebra 2. So anytime we have either a rational function or any function where plugging in a value yields a number divided by 0, we're at the location of a vertical asymptote. And then lastly, we'll talk about jumps as they're associated with boundaries of piecewise functions. That's where we see a jump. Of these first 2 examples on this page, let's just look at this function h. We're asked to describe the domain of the function and any discontinuities. So if we were to factor the numerator of h, that would yield t minus 7 times t plus 1 over t minus 7. I picked this one because factored form is sometimes necessary to understand what's going on. So this is a rational function, and the domain of this would be all real numbers, except we do have a discontinuity. So if I remember from our earlier days of class, that if I have a 0 in my denominator, that's going to cause a discontinuity. So I know that if t minus 7 equals 0, that happens at the value t equals 7. So at t equals 7, there's something going on here. So if I also notice that t minus 7 is a factor of my numerator when I write that in factored form, if I plug in a 7 either to my numerator in factored form or just over here to my original numerator, that's going to also yield 0. So because plugging in or substituting 7 for t yields 0 over 0, this function has a hole in the graph at t equals 7. So there's a hole in the graph at t equals 7. Otherwise, h would exist on the domain or would exist for all real numbers. So when we're talking about the domain of h, we could say that the domain is from negative infinity up until 7, and then on the other side of 7, from 7 to infinity. So this notation just excludes the value t equals 7, and the discontinuity we observe there is a whole. All right, let's look at this next example. Let's maybe just look at f. So in this example, we are asked to determine the domain and describe any discontinuities, so the same idea. But this is a piecewise function, so we're going to have to really kind of think about this one. So first of all, in the top piece of f, where I have x over x minus 2, if I think about what values would cause a problem in our domain here, well, we're really just concerned with the denominator, because again, we can't divide by 0. So if I consider where x minus 2 equals 0, that would be where x equals 2. That value would be problematic. However, if we look at the boundary of our piecewise function, we would never substitute a 2 into the top piece. So we would only substitute negative numbers into the top piece. Or in other words, f is defined as x over x minus 2 for all values of x less than 0. So we don't actually have any concerns with that top part of our function. So now let's look at, and you don't have to scratch that out in your example necessarily, but all right, let's look at the bottom piece where we now have the natural log of x plus 1. And again, we said in the first section of this unit that the argument of a logarithm must be positive. So when I use the word argument, that's just the thing I'm plugging into a function. So that means that x plus 1 must be positive, so must be greater than 0, which means that x must be greater than negative 1. So again, this is not really a concern for us because negative 1 is not greater than or equal to 0. So we're never going to plug a negative 1 into this function. So far, we have ruled out that this function has any vertical asymptotes or holes. Like there's nothing causing me to get a 0 over 0 or a number over 0. We don't find any domain issues with those pieces, but we need to also check for jumps. So going back up here, we're told that a jump occurs at the boundary of a piecewise function if the limit from the left and the limit from the right do not agree. And we talked about that graphically as well. So we need to evaluate the limit of this function f from the left and the right at the boundary of the piecewise. So to do that, I'm going to write the limit of f of x. The boundary is where we switch pieces. So this piecewise only has a boundary at x equals 0. So I want to come up on the left-hand side, and when I am approaching this, when I'm approaching x equals 0 from the left, I'm using the top piece of the piecewise function because that is for values of x that are less than 0. So as I consider that, I'm going to just start with plugging 0 in. So I get 0 over 0 minus 2, which is 0. So on the left-hand side, this has a limit of 0, or as we approach 0 from the left, f has a limit of 0. We also need to consider the right-hand side. So as we approach 0 from the right, we're using the bottom piece of our function because values to the right of 0 are greater than or equal to 0. So we're going to plug this in to the natural log of 0 plus 1. Well, x plus 1, we're going to substitute a 0, and that is the natural log of 1, which is 0. So because these limits agree, there are no jumps. There's not a jump here in this piecewise function. The domain of this function f is all real numbers. So just to get an idea of what this function f looks like, I went ahead and graphed it in Desmos. I always have to Google how to graph a piecewise function in Desmos. I never remember. So it looks a little funky, but if you look at that left-hand side in red, that is the piece that is x over x minus 2. So that's part of that rational function. And then the right-hand side in blue is the natural log of x plus 1. And as we can see, this function exists for all of those values. And you can kind of play around with it, but we should know from algebra 2 or remember a little bit what that end behavior is going to look like there. So okay, so all that to say, sometimes it helps to see that representation. All right, we're going to pick up in the next video with just how to evaluate these different types of limits.